Okay, so this is problem 1250, and in that problem, we're being referred to this amplifier where we have a V in, and that's going through a couple of error. What these are called error amplifiers, and each of them have a gain mu, and then so here we have a PMOS, and here we have a load, and here we have some feedback here, and then our input is going into the error amplifiers here. So, and we are asked a number of questions about this design, and this is a very practical design. So I want to thank Jonathan for requesting this. It has a lot of good applications, and if you have the right MOSFETs, you can really drive pretty large loads just by making those transistors large. It is an AB configuration, so it has good linearity with decent efficiency. So this is a very practical design. So the thing to remember is that these amplifiers here, these error amplifiers, are an abstraction. Those are not op amps. So basically, each of those, so essentially, those are difference amplifiers that may look like this. So this would be the positive input, this would be the negative input. And so essentially what is inside those mu boxes is this. And the gain, so the gain mu for this is equal to RF over RI. And then the output voltage is RF over RI times the difference of the input voltages at the plus and minus terminals. Okay, so we're going to be asking this problem to calculate mu, and we're going to see that that's equal to 10. Yeah, so you could make that by making something like that. Okay, so that's what we're going to be looking at. They give us a number of parameters, and the first thing that they ask us to do is to calculate the width and length ratio or each of the external MOSFETs, the P and the N. And the actual design characteristics and the equations for this design is derived in the part of the book where the figure is. So you do have to use that and refer to it. So, but to calculate the width and length ratio of each of the transistor, which is part A of that, we use the drain equation for the transistors. So for the quiescent value, and that's going to be 1/2 K prime W over L of times the overdrive voltage square. Okay, so we're giving all these parameters. We're told that the quiescent current is 1.5 milliamps, and remember that if we work in currents in milliamp and voltage in volts and resistances in kilo ohms, then the units are consistent per Ohm's law. So here we can formulate this equation, and for K prime for P, for the PMOS is 0.1. So here we have the width to length ratio for the PMOS. And we're also told that the overdrive voltage is 0.15 volts. So here we have this equation, so straightforward. And we can see that the width to length ratio of the PMOS comes out to be this figure, okay?
Dr. Hernandez?
Yeah.
I'm sorry, I just wanted to ask if you let Connor in from the waiting room.
All right. Now we're also told that, and we could have used the equation for the N channel and found the width to length ratio for the N, and then found the P. But now that we have the P, we're also told that the transistors are matched. So what it means to have matched transistors is that this proportion this proportion holds, that the K prime for the N over the K prime for the P is equal to the ratio of the width to length of the transistors. That's what it means for the transistor to be matched, because what you're doing is, what makes the K primes mismatch is the fact that the K is proportional to the mobility of the majority charge carriers. So in the case of the N channel is going to be electrons, in the case of the P channel is going to be holes, and the holes have lower mobility. So the electrons are stronger in terms of carrying charge. So what that means is that the K prime for N is going to be the K prime for the N is going to be higher than the K prime for the P. So you have then to make the width to length ratio of the P higher to compensate for that. So you have to make the P channel stronger by making the width of the channel, which is how big you make the transistor, and you have to make that higher. So that's what this, when you have that transistors are matched, that's what it means. So since we have everything else here except the width to length ratio of the N channel, we can use that proportion to calculate it. And the one thing to remember also is that these are the electrical width and length of the channel. It's not really the width and length of the transistor, which is a geometric characteristic. So essentially, if you were looking at the transistor in sort of some 3D configuration here. So where this is the source and this is the gate over here. The electrical length of the channel is this, okay? And then the width would be this, this dimension. But geometrically, when you're drawing the transistor, we call this the length of the transistor. We call this the length of the transistor because that's when you draw the polysilicon. When you draw a transistor, you draw it with that length of the polysilicon, and this become the width of the polysilicon because this is the critical dimension. So when you hear about a 3 nanometer technology node or something like that, they're basically saying that this is 3 nanometers, and that's the width of the polysilicon as the transistor gets constructed. So that's something to keep in mind as we go into the next chapter, which is about the integrated circuit design of analog circuits. So now we can calculate with this proportion the width to length ratio of the N channel. So let's do that. So that's going to be the width to length ratio of the P channel that we calculated before, divided by the ratio of the K primes. And that ratio is 2.5. We're given both K primes. So we have that the width to length ratio of the N channel is this quantity. So you can see that the N channel is much smaller than the P channel transistor, and that's to account by the fact that the P channel is weaker, so you have to make it larger. So that takes care of point A, and then the question B, or part B, it says that specify the required value for mu. So that is essentially the gain of the error amplifiers, okay? And again, this design was derived and analyzed in the book in that section. So we have to refer to those equations. And the main equation that we can use from that derivation, that analysis, is that the GM of the transistor, and they're going to be the same because the transistors are matched. So this is going to become very important throughout this exercise because we're going to rely on that fact that the transistors are matched, and then that makes the design symmetrical in terms of what the P channel is doing and what the N channel is doing. So we have this equation that holds for this design. So we can find the required GM, the transconductance for the transistors. So here we have 2, and the quiescent current is 1.5 milliamps, and the overdrive voltage is 1.5 volts, or 0.15 volts rather, and that gives us that the transconductance is 20 milliamps per volts. Then another equation that applies to this design that was derived during the analysis is that the output resistance of the amplifier is equal to the overdrive voltage divided by for mu, the gain of the error amplifiers times the quiescent current, okay? But here we see that we have this ratio of V over drive over IQ, which is here, okay? So if we substitute for that ratio of V over drive over IQ in this equation, using this one over here, we get that R out is 2 mu times GM, which we already know. And we are given the output resistance of the amplifier, okay? Now, again, because the transistors are matched, GMP is equal to GMN and just equals to GM, which we have here already. So using this equation over here, so that's equal to R out, then we can derive mu, and that is going to be equal to 2 GM R out, and we have all those quantities, so that's going to be equal to 2 times 20 times 10 to the minus 3, because we have milliamps per volt. And here we're going, because we have a very small R out, okay, which is 2.5 ohms. So that's what we have to express the GM in amps, in this case, to keep the units consistent. So that gives us that mu is 10 volts per volts. So that's why, as I mentioned, the gain of the error amplifiers is 10. And that takes care of point B. So let's look at what they're asking for C. They are asking what is the expected error in this in the stage for the gain, the expected error there. So the overall gain of this power amplifier. So this is going to be C. And again, when we derived, when this circuit was analyzed, and again, that's in the book, we see that the actual gain is going to be RL divided by RL plus R out. And remember that this is a power amplifier, so we're basically aiming for a voltage gain of overall. We're aiming for a voltage gain of 1. What we're going to be driving our current or providing is a current load, current to the load. So the voltage gain is going to be close to 1, but it's going to be degraded by the relationship of the load and R out. There's nothing you can do about that with this topology. And if you have a sense for your load, for the load that you need to drive, which you usually do, then you just need to ensure that the output resistance of the amplifier stage, the overall amplifier stage, R out, is much smaller, because you don't want to, you want to be close to 1. And the closer you are to 1, the more efficient the overall amplifier is. So we are told that the load is 50 ohms. So, and that the target R out is 2.5 ohms. So that gives us a gain of 0.952. So the gain error, which is what we are asked to calculate, the gain error is how far we are from 1. So that is 0.048, which is in turn a minus 4.8% error. So that is part C. And then let's go to part D. Let's see what they're asking in part D. In part D, they're saying that in the quiescent state, what DC voltage must appear at the output of each of the error amplifiers. So basically driving the gate, the gates of the PMOS and NMOS. So the thing to observe here is this. So in the quiescent state, the DC voltage at the output of each, I'm just going to call it the mu amp, must be such that the current, the drain current of each of the driver transistors, so that would be IN and IP are IQ, right? Because that we are in the quiescent state. So if we look at the P case, if we look at the P case, what that means is that the voltage from source to gate down from VDD, that can be also expressed as VDD minus the threshold for the P channel minus the overdrive voltage for the P channel. And we're given these parameters. We know VDD, we know that the threshold voltage, and we also know the overdrive voltage. Okay, so we just need to find that out. So VDD minus VSG. VDD is 2.5. The threshold voltage is 0.5 volts. And the overdrive voltage is 0.15 volts. So that gives us that the difference, or the actual voltage at the gate, which is down from VDD, is 1.85 volts. And we can do the same thing for the end stage. So for the end stage, for the QN amplifier, we have that minus VSS. So this is looking at the voltage at the source of the N channel, plus VGS, gate to source voltage. At the gate of the N channel is going to be minus VSS plus the threshold voltage for the N plus the overdrive voltage for the transistor, which are all the same. And so that gives us that minus 2.5, which is VSS is the same as VDD, plus 0.5 plus 0.15, and that gives us minus 1.85 volts. So you can see that for the P channel, we got at the gate 1.85 volts, and for the N channel, we have minus 1.85. So you can see the symmetric nature of the design because the transistors are matched. Okay. So that was D. Now let's look at question E. Let's see what that is. So question E says, at what value of positive V out will QP be supplying all the load current, and then repeat for negative V out and for QN when QN is supplying all the current. So we want to what value of V out these transistors start taking over and supplying all the current to the load. So let's see. So that's when each transistor respectively gets is essentially starts getting into saturation. Okay. So that condition, so let's say E, that condition QP supplies or starts supplying all the load current. That's when QP starts getting into saturation, but more importantly, when QN is cut off. So when QN is off. When we have that condition, and again, this is an equation, the two equations that we're going to be using have to do with the derivation of this specific design. So they are in that specific part of the book. We have that the drain current for the N channel is given by this expression. So if this is 0, okay, what that implies is that mu that implies this this expression here. Okay. So if you make IDN 0, you can derive this expression over here. And then similarly, we have for the P channel, for this specific design, we also have this derived expression. Okay. And then if we substitute what we had before into this expression, what we got from the IDN expression, we have that oops, I'm gonna get this right. And that's what I want. So that means that the current being supplied by the N channel when the P channel, by the P channel when the N channel cuts off is 4 IQ. So 4 times the quiescent current. Okay. And since all the load current, since at that point, the load current is equal to the current supplied by the P channel, then which is 4 IQ here. So we have this expression here. Then the output voltage across the load is going to be 4 IQ times the load resistance, and that is 4 times 1.5 times 10 to the minus 3, because that's we're going to express the load resistance in ohms, not in kilo ohms, so we have to express IQ in amps, so 1.5 milliamps times the load resistance, and then we get that the output voltage when QN cuts off and QP starts providing all the current to the load is 0.3 volts from this expression over here. And since the design is symmetric, you'll find that the output voltage when the P channel cuts off and the N channel starts supplying all the current to the load is simply then in that case minus 0.3 volts. Again, because the design is symmetric. Okay. Okay, so now the last point that they ask us for is F. So they ask us what is the linear range of VO, okay? So that is when actually each transistor is going to be supplying all the load, but they're not just getting into cutoff or saturation. The transistor supplying the load is deep in saturation. So the voltage from drain to source of each transistor when it's supplying that load is very small, and then it's going to make the load, the voltage across the load, the highest. So that gives you the highest linear range of the amplifier. Okay. So essentially, what we're looking for is what is that output voltage, which we're going to call VO max. So let's look at the P channel case. Now for that, what is helpful is to look at that P channel case where we have our error amplifier here, and we have our V-in. Now for the V-out max, the V-in is the corresponding V-in max. And so here we have the M part. We're not going to draw that, but we do want to draw the P channel part. And here, so we said that at that point, the P channel is deep into saturation and the N channel is deeply cut off. So the current here is going to be 0. And here we're going to have an IDP that is being supplied all to the load. And that is 50 ohms. So that at that point, the voltage here is our VO max that we want to find, and the current through here is going to be our IL max. Here we have VDD, that's 2.5 volts. And another observation in this circuit is that when that happens, okay? For this P channel to be as saturated as possible, what we're going to need to have from the source to the drain is the maximum overdrive voltage for the P channel, okay? And what that means is that from the drain to the gate of the P channel, here we have the absolute value of the threshold voltage with this polarity. And the voltage here at the gate of the P channel, here, the voltage here is going to be the output voltage max minus the threshold voltage for the P channel. So that's the situation that we experience when we're getting the maximum voltage in the topology. And then with this knowledge, we can go back and then formulate the drain equation or the IDP equation for the P channel. Just working with that half of the circuit at this point. So let me get rid of this beautiful drawing now and just formulate that equation for the P channel. So minus VGS is just the same as VSG, which normally we would write. I just like VGS, but I have to put a minus there. So that basically, this is the overdrive. This is the maximum overdrive voltage. Okay. So this applies. This is for VO max. So then I can solve this equation. So remember that this IDP is the maximum current IL max, but we have to find VO max. So I'm going to get rid of IDP, which is the same as VO max over RL. And this is going to be, if I use what I formulated, let's see here. Let me put this part here, because this is multiplying what is going to be above, but it's kind of long. So if I use the voltage that I wrote in the previous drawing, what goes here is this, because I need to put it in quantities that I have, and at the same time find the value of VO max. Okay, so that gives me essentially a nice quadratic equation on VO max. So that's going to be VO max divided by So now I'm going to be working with kilo ohms, milliamps, and volts. So in kilo ohms, RL is 0.05 or 50 ohms. This is K prime. We had calculated the width to length ratio, electrical width to length ratio of the channel for the P channel as 133.3 times 2.5. So all that inside the square part reduces to this. Okay. So if I multiply across by 0.05, I get that VO max is equal to times 6.25 minus 5 VO max plus VO max square. So I just basically expanded this and did some combination of terms. And finally, to get my my nice quadratic equation, I rearranged this a little bit and I just get that 3.33 VO max square minus 17.67 VO max plus 20.83 is equal to 0. So then I can essentially use the quadratic equation to solve for the possible values of VO max. So I have that VO max is plus 17.67 divided by 6.67 plus or minus 17.67 square minus 4 times 3.33 times 20.83. So that is inside the square root, and that is divided by 0.67. So then I get that the possible values of VO max are 3.53 and 1.77. So obviously this is not valid because VDD is 2.5. So I can never have an output voltage that is greater than VDD. So our VO max is going to be 1.77 volts. And then by symmetry, my VO min, which is when the N channel is in deep saturation and the P channel is deeply cut off, then it's going to be minus 1.77 volts. So I have a swing of VDD of 5 volts plus or minus 2.5, and I have about a bit above 3 volts of swing for this for the output, for the linear region of the output, and that also is related to the efficiency. Okay, so the closer I get to the rails, the more efficient the circuit is. So you can see that from a linearity perspective, the efficiency is not 100%, and it shouldn't be because it's a class AB amplifier. So that concludes problem 1250.